let's state the special properties of conditional expectation again and give the proof of that. Special properties of conditional expectation. Consider f and g subsigma algebras of H. W and X measurable with respect to H. We define, well, such that their mean, there exists the expectation of X and the expectation of W. Then we have conditional determinism, which says that if W is f measurable, expectation given f of W times X, we can take W out. Since it's measurable, it means we can know its value, so this can be put in front. Basically, this is W, which multiplies the conditional expectation of X. And then the tower property, the expectation given G of the expectation given F of X. This is the same as this, and at the end of the day, the expectation of F wins when F is smaller than G. And this is the tower property. Proof. For the first point, consider X positive and measurable. We already know, W is F measurable and positive, because by assumption here we have that T is in F. Well, we don't assume it's positive, but here it says that this means that X bar, being the conditional expectation of X, is F measurable. And now consider this thing, the expectation of V times Wx which can be also seen in this way, multiplying first V and W and then X. This thing is F measurable and positive. And this, by a previous result that we have seen, is the same as this, which again can be grouped in a different way as W times X bar for any V, F measurable and positive. As W times the conditional expectation of X is, well, this thing. Is a version of the conditional conditional expectation given f of w times x. Nothing too obscure, even if I don't remember the previous, it was expectation it was something like this, I think, the previous result we have seen. But I still don't understand. Here we don't take out anything. Cool. For the second point, consider f sub sigma algebra of G. X measurable and positive with respect to H, and W, capital W, which is the conditional expectation. Okay. Given f of x, which is positive and measurable with respect to f. Now this means that W is also G measurable and positive, and again by conditional determinism this is W, hence let's call this thing Y. Why? Why do we call it Y? I don't know. Here it's put like this, and here this is called x bar. Now x bar this, so measurability is satisfied. Now to check the projection property, consider V and since x is a version of the conditional expectation of x, we have that the expectation of V times the conditional expectation is the same as this for any V. Now recall that Y, we defined it to be the conditional expectation given the sigma algebra G of X, which is G measurable, and notice that V is F measurable, which is in turn G measurable, so V is also G measurable. Now for Y we have the expectation V times Y, expectation V times X for any V. And especially for those that are F measurable, hence this is why. So X is a version of this thing. Now we have another important theorem. This thing is not completely clear. I will have to review it again, but not now. I don't feel like it. Now it's time for conditioning as a projection for any X in L2. There exists a unique autoequivalence X bar in L2 of F such that the expectation of the square in absolute value of the difference, I don't know how, but of the difference in absolute value between X and X bar squared is the infimum over the random variables in L2 of F such, well, of the expectation so for any X in L2 there exists a unique autoequivalence variable X still in L2 which minimizes the, whoops, where is the pointer? The distance from X. And X minus X bar is orthogonal to L2 of F, which means that for any V in L2 of F, the expectation of V which multiplies X minus X0, X bar is 0. Now as a remark, X bar is the orthogonal projection of X into or onto L2 of f and onto f. Well, L2 of f. And we have the decomposition x equal x bar plus x tilde. Yes. Which I don't remember very well. Let's take a look at the proof. Now let x, the true norm of x, the L2, well, but we have this. Okay, as norm, we will simply leave the number. So this should be the true norm of x. This is the square root of the expectation of x squared, I think. Yes. Fix x in L2. Fix x in L2 of f of h. And define delta to be the infimum over the random variables L2 of f such that x minus y. So the random variable which minimizes this norm, let yn be a sequence in L2 of f such that delta n defined as xn minus yn, or x, no, okay, this goes to 0 as n grows, not to delta. Now let us prove that yn is Cauchy. In L2. Yn minus ym squared is 2 x minus ym squared plus this. Minus 4 times, I'm basically mindlessly copying what is written here. I have no idea what I'm writing. X minus 1/2 ym minus plus yn. Well, and all, okay. And this thing is in L2, it says. Taking the expectation two times the expectation, okay, no. We directly bound this by 2 delta m squared Oh, this is the projection theorem basically, in view, like with random variables instead of inner products. Okay, I think. Then we will see that the two deltas go to 0 maybe in some way. Minus 4 delta squared. And taking the limit, well, here it says that it is like this. As there exists x bar in L2 of f such that this happens. And here it says that x bar is unique up to equivalence by definition of the L2 norm, and the fact that x bar is in L2 implies that x minus x bar is greater than delta y This is the limit as m and n. Now Minkowski tells us the norm of x minus x bar is bounded by x minus yn, right? Plus the norm of yn minus x bar, which goes to delta plus 0. That is delta. So we have that this is delta. This is bounded by delta. Well, here it says it's equal. And now for v in L2. And the real number a. Since the expectation of this difference squared is delta squared, then I think here we are, I don't know, then we simply have this a squared, the expectation of v squared minus 2a, the expectation of v that multiplies x minus x bar, plus delta squared. I don't know why this is the case, but let's just keep writing until the end at this point. AV plus minus x bar squared, which is again x minus AV plus x bar. This thing is in L2. And this is greater than delta squared. And to conclude, a squared times the expectation v squared minus 2a expectation of v times this is greater or equal than 0 for any a, because the two deltas cancel out. For any a, zero for any a in R, which is impossible unless expectation of v x minus x bar is 0. And this concludes the proof, which I simply rewrote mindlessly without understanding anything. I think my brain is kind of out of energy today. I mean, at least now. Maybe we will review this next time, or we just will skip to the next point, which is conditional expectation given random variables. But quite tricky. Let's just pause or stop directly for today.